The spring of 1940 presented Britain with a mathematical dilemma no one wanted to face. RAF Bomber Command was sending crews over occupied Europe in aircraft that shared one fatal trait. They were slower than the Messerschmitt Bf-109s hunting them. The Bristol Blenheim, backbone of the light bomber force, could barely reach 266 miles per hour, while German fighters cruised at 354. That 88 miles per hour gap often meant the difference between returning home or becoming a name in the Air Ministry's steadily worsening casualty lists. Between May and September 1940, Bomber Command lost 330 aircraft. Each statistic represented men who had climbed into Blenheims, Wellingtons, or Hamdens knowing full well they were boarding machines the enemy could catch, attack, and destroy almost at leisure. The standard fix was predictable: add more guns, dorsal turrets, ventral guns, side mounts. Each new weapon added drag and weight, paradoxically making the bombers even easier to intercept. Engineers were caught in a vicious loop. More protection meant less speed, and less speed meant more losses. The Air Ministry solution followed the same orthodoxy. If bombers couldn't outrun fighters, they must endure them, add armor, protect crew compartments, reinforce fuel tanks, strengthen the frames. By mid-1940, proposals circulated in Whitehall calling for bombers laden with up to half a ton of armor plate. But physics is indifferent to bureaucracy. Every pound of steel required additional aluminum structure to support it. Engines worked harder, fuel burned faster, and operational range shrank. Then came a new crisis: aluminum itself. Britain's supply relied heavily on imports, especially from Canada and the United States, but German U-boats were turning the Atlantic into a graveyard for shipping. In June 1940, the War Cabinet received chilling forecasts. Existing aluminum stockpiles could sustain production for perhaps 18 months. After that, Britain's aircraft industry might grind to a halt, not from German bombs, but from lack of metal. The newly formed Ministry of Aircraft Production, under Lord Beaverbrook's relentless urgency, faced impossible trade-offs. Heavily armored bombers consumed huge quantities of aluminum, but offered marginal survival benefits. Lighter bombers saved material but doomed crews. Fighter production alone devoured metal. Each Spitfire needed roughly half a ton of alloy, while bombers required several times that. The upcoming Avro Manchester demanded 3,200 pounds of aluminum for its A-frame alone. Whitehall engineers began exploring options that once sounded absurd. Could they build bombers from steel? Too heavy? From fabric and wood, like Great War biplanes, hopelessly obsolete? A few dared to whisper about hybrid or composite structures that could save metal without sacrificing performance, but most dismissed such notions as desperation masquerading as design. By autumn 1940, Britain's strategic equation had become brutal in its simplicity. The RAF needed bombers that could strike Germany and survive. Survival meant either armor, consuming resources Britain didn't have, or speed, which seemed physically unattainable within accepted design limits. Into this impasse walked Geoffrey de Havilland. He had built his first aircraft in 1909 in a rented shed and destroyed it on its first flight, but decades of trial and error had forged him into one of Britain's most resourceful engineers. His company had produced the DH.4, the Great War's finest light bomber, and the Moth series that made flying accessible across the empire. So when de Havilland appeared before the Air Ministry in October 1939 proposing to build a high-speed bomber made entirely of wood, officials quietly wondered if the 57-year-old designer had finally gone mad. To them, the idea reeked of nostalgia, would belong to the 1920s, to barnstorming biplanes and weekend flying clubs. Serious military aircraft were metal, durable, standardized, modern. The Americans built all-metal bombers. The Germans built all-metal bombers. Even the reserve-starved Soviets were turning to aluminum. A wooden bomber sounded as ridiculous as cavalry charging panzers. The objections came swiftly and scornfully. Wood, they said, rotted, warped with humidity, and couldn't endure high-speed aerodynamic stress or vibration. It was too heavy. Everyone knew metal was lighter and stronger. Wood couldn't be mass-produced with precision. Most damning of all, it felt old-fashioned, a relic of an era before stress-skin construction defined modern flight. Yet de Havilland knew something his critics didn't, that necessity, not orthodoxy, would soon rewrite the rules of aircraft design. Skin construction and cantilever wings were the gold standard of modern aviation, and one Air Ministry engineer reportedly quipped that building wooden bombers made as much sense as arming infantry with longbows. De Havilland's counter-arguments leaned on facts the bureaucrats didn't want to confront. Britain had vast timber resources, Canadian spruce, birch, and mahogany, abundant and easy to ship. Wood didn't require the rolling mills, extrusion presses, or heat treatment plants that aluminum production demanded. Across Britain, furniture factories sat idle, their skilled craftsmen underused as wartime priorities diverted materials elsewhere. Those workshops, he argued, could be repurposed overnight to build aircraft parts using methods they had mastered for generations. A wooden bomber wouldn't compete with Spitfires and Hurricanes for scarce aluminum, and that alone made it worth attempting. More importantly, de Havilland understood what metal-focused officials had forgotten. Modern wooden construction had evolved far beyond the crude trusses of the Great War. His engineers had developed a laminated sandwich structure, 3 layers, birch plywood on both outer faces with balsa wood core in between, bonded using advanced caesium-based adhesives under heat and pressure. The result achieved strength-to-weight ratios rivaling, and in some areas exceeding, aluminum alloy. The geodetic molding process they devised created compound curves that were simultaneously light, rigid, and durable. Yet the Air Ministry was unmoved. In December 1939, they rejected the design outright. Too experimental, too risky, too reliant on a material associated with furniture, not fighters. But de Havilland refused to give up. He knew his company's survival depended on military orders. Yet beyond commerce, he believed in the concept. A wooden bomber could outperform anything then flying, if only he could build it. He revised the proposal, sharpened the performance figures, and resubmitted it in March 1940. The second rejection came in May, even as Dunkirk's evacuation exposed Britain's dire need for innovation. Unwilling to quit, de Havilland made one final appeal in July 1940, during the opening weeks of the Battle of Britain. This time, he made a staggering promise. The wooden bomber would fly faster than a Spitfire Mk2. Officials treated the claim as fantasy, filing it alongside perpetual motion machines and alchemist dreams. Still, to quiet his persistence, they approved a single prototype order in November 1940, an experiment expected to fail quietly. At Salisbury Hall, a requisitioned manor house in Hertfordshire, the prototype began taking shape. Instead of riveters hammering aluminum skins onto frames, craftsmen were gluing wood layers inside giant molds that looked more like furniture presses and aircraft jigs. The process drew on skills cabinet makers knew instinctively, but which made aeronautical engineers uneasy. The secret was in the sandwich. Engineers used birch plywood for the outer layers, thin veneers laminated with alternating grain directions to multiply strength. Between them, they inserted balsa wood from Ecuador, lighter than cork, yet astonishingly resistant to compression. The result? 3-ply birch, half-inch balsa, 3-ply birch again, produce a panel roughly 3/4 of an inch thick, 40% lighter than aluminum of comparable strength. The adhesive was equally vital. De Havilland chemists refined a casein-based resin, a milk protein glue, that bonded stronger than the wood itself. Under heat and pressure, it soaked into the fibers and cross-linked into a tough matrix, distributing stress evenly rather than concentrating it at rivet holes. Unlike metal skins, which crack from fatigue at fasteners, the laminated would absorb vibration and stop cracks dead at each layer. The geodetic molding method revolutionized shaping. Instead of forcing flat panels to bend, a process that introduced internal stress, de Havilland's team mold curved sections directly to their final form. Inflatable rubber bags applied uniform pressure as the glue cured in heated presses, producing perfect aerodynamic contees. Each fuselage half, port and starboard, was molded in one seamless operation. The resulting monocoque required no heavy internal frame. The shell itself provided rigidity. This gave the aircraft an unmatched aerodynamic smoothness. No rivets to disturb the airflow, no seams to create turbulence, no protrusions to cause drag. Critics who had mocked Wood's weight now faced the irony that the Mosquito's A-frame came out lighter than its metal rivals. Its empty weight was 14,300 pounds, over 1,000 less than the aluminum Bristol Beaufighter, despite the Mosquito being slightly larger. De Havilland had just disproved an entire generation's assumptions about what modern aircraft could be built from and what obsolete materials could still achieve when used with imagination. The wooden bomber had somehow overturned the long-held metal is light assumption through superior structural design. Temperature variations that warped aluminum caused no issues for properly treated timber. The laminated shell expanded and contracted uniformly across its layers, while metal panels attached to rigid frames expanded unevenly, creating stress and buckling. Air Ministry engineers fretted about humidity, but tests showed the casein adhesives remained stable from -40 degrees Celsius to +50 degrees Celsius. The multiple plywood skins shielded the balsa core effectively. Moisture penetration would take months of neglect, not hours of flight. The nose section showcased the construction's flexibility. Molded as a separate unit, it attached to the fuselage with reinforced joints that could be detached for servicing. Different nose modules, bomber, fighter, or reconnaissance, could be swapped onto the same A-frame. A metal aircraft would have needed cutting and riveting, which simply bolted together. The prototype rolled out of Salisbury Hall's improvised assembly line on the 19th of November, 1940, painted training yellow and designated W4050. Geoffrey de Havilland assigned his chief test pilot, his 27-year-old son, also named Geoffrey, to perform the maiden flight. The younger de Havilland had logged thousands of hours testing everything from moths to racing planes, yet even he doubted plywood could bear the stresses his father's equations promised. The first flight took place on the 25th of November, 1940 at Hatfield Aerodrome. De Havilland Jr. lifted W4050 smoothly into the cold autumn air, the twin Rolls-Royce Merlin engines pulling the yellow aircraft off the grass with startling ease. Observers expected a lumbering takeoff. Instead, the Mosquito climbed cleanly and fast. For 28 minutes he tested handling, control response, and the structure's feel under load. When he landed, his report was just 3 words: fast as hell. Formal trials began in February 1941 at Boscombe Down, the RAF's rigorous test center, where evaluators greeted every manufacturer's claim with healthy skepticism. They had heard grand promises before: fighters that couldn't turn, bombers that couldn't climb, reconnaissance planes that couldn't see. De Havilland's wooden wonder arrived boasting speeds greater than the Spitfires. The test pilots expected humiliation. Instead, they found astonishment. At 15,000 feet, fully loaded, W4050 reached 388 miles per hour. Assuming error, they recalibrated instruments and tried again. At 22,000 feet, the Mosquito touched 392 miles per hour. For comparison, the frontline Spitfire Mk2 managed 370 miles per hour, the Hurricane about 340. Every German fighter then in service, except the forthcoming Focke-Wulf FW-190, still months from combat, was slower than this supposed bomber built from furniture. The results demolished the accepted hierarchy of air warfare. Bombers were meant to be slow, fighters fast. There had been doctrine since 1918. The Mosquito ignored it entirely. Here was an aircraft able to deliver a 2,000-pound bomb load to Berlin and back without a single gun, because nothing the Luftwaffe flew could catch it. Its advantage came not from exotic engines or secret propellers, but from aerodynamic perfection made possible by smooth wooden construction. Air Ministry officials who had mocked the idea now faced arithmetic they couldn't refute. A Bristol Blenheim required 6 crew: pilot, navigator, bomber, wireless operator, and 2 gunners. The Mosquito needed only 2. The Blenheim carried 3 tons of bombs at 266 miles per hour. The Mosquito carried 2 tons at nearly 390 miles per hour, hit targets with greater accuracy thanks to visibility, and returned home before interceptors even arrived. Which was a better weapon? Another revelation came in handling. Test pilots assumed the wooden bomber would feel heavy, like a lorry. Instead, it flew like a fighter. Controls crisp, turns tight, response immediate. Its 14,300 pounds empty weight helped, but so did the rigidity of its monocoque body. Metal A-frames flexed slightly under G-forces, introducing lag between control and motion. The Mosquito barely twisted at all, moved the stick, and the aircraft obeyed instantly. By March 1941, Boscombe Down's official report confirmed what pilots were already saying. The Mosquito represented the most important advance in combat aircraft design since the invention of stress skin construction. The Air Ministry, after 18 months of rejections, now faced an awkward truth. They had nearly killed the RAF's most capable bomber before it was born. The first operational unit, No. 105 Squadron, began receiving aircraft in November 1941, exactly 1 year after the prototype's first flight. The Air Ministry finally approved production, though cautiously. Initial orders totaled just 150 planes, reflecting lingering suspicion that might fail in battle. Squadron leader Reggie Reynolds was among the first to prove them wrong. Commanding No. 105 Squadron, Squadron leader Reggie Reynolds received his new orders, and with them, an aircraft unlike any bomber he had ever flown. No gun turrets, no armor plating, no defensive weapons at all. Just speed, a bomb bay, and a conviction that escaping combat was smarter than enduring it. The squadron's first mission launched on the 31st of May, 1942, targeting Cologne. 4 Mosquitoes lifted from RAF Maham, each carrying 4 500-pound bombs for a daylight precision strike on the Matford Motorworks. The Luftwaffe had standing orders to intercept any RAF bombers crossing German airspace in daylight. Messerschmitt Bf-109s and Focke-Wulf Fw-190 scrambled from multiple fields as radar stations tracked the intruders. What followed proved that speed mattered far more than guns. The Mosquitoes crossed the channel at 25,000 feet, cruising comfortably at 320 miles per hour without even straining their engines. German controllers vectored interceptors toward them. On paper, the Fw-190, the Luftwaffe fastest fighter, could reach roughly 408 miles per hour, seemingly fast enough to intercept. But when the fighters began closing, the Mosquito pilots advanced throttles to maximum continuous power, climbing slightly and accelerating to nearly 380 miles per hour. The German pilots found themselves locked in a losing chase, close enough to glimpse the wooden bombers ahead, yet never able to close the distance before fuel reserves forced them to turn back. All 4 Mosquitoes reached Cologne, dropped their bomb precisely, photographed the impact, and returned home untouched. The contrast of conventional operations was staggering. A Lancaster raid on the same city the night before had lost 41 out of 1,047 aircraft, a 3.9% loss rate that would have cost at least 1 Mosquito, had the odds applied. Instead, the Havilland's wooden bombers achieved the impossible, 0 losses. And it wasn't a fluke. On the 25th of September, 1942, a single Mosquito flown by squadron leader Perry struck Gestapo headquarters in Oslo. Flying low through mountain valleys, using terrain for cover and sheer speed for defense, he destroyed the building during a meeting of senior German officers and escaped before interceptors were airborne. Luftwaffe pilots began reporting an infuriating new phenomenon. British bombers were appearing over German targets, attacking, and disappearing before fighters could react. The standing orders, climb, intercept, engage, no longer work against aircraft that could simply accelerate out of range. Years of German fighter doctrine had rested on one assumption: bombers were slower than fighters. The Mosquito shattered that logic completely. By early 1943, Mosquito squadrons were conducting regular daylight raids deep inside Germany, missions considered suicidal for any other bomber type. On the 30th of January, 1943, 3 Mosquitoes executed perhaps the most symbolic strike of the war, a daylight raid on Berlin timed precisely with Reichsmarschall Hermann Göring's scheduled radio address marking the Nazis' 10th anniversary in power. As Göring began to speak, bombs detonated nearby, cutting the broadcast mid-sentence. The physical damage was minor, but the psychological effect immense. If wooden British bombers could strike Berlin in daylight and escape unscathed, what faith could anyone have in German air defenses? The Mosquito's versatility quickly became apparent. The original bomber configuration, 2 crew, 2,000 pounds bomb load, no defensive guns, was only the beginning. The A-frame proved so strong, so aerodynamically clean, that engineers could re-engineer it endlessly without losing its performance edge. The first major adaptation was the night fighter variant. The bomb bay was replaced with an AI-Mk4 radar set housed in the nose. 4 20mm Hispano cannons were fitted beneath the cockpit and 4.303 Browning machine guns in the nose, creating a fighter faster than anything flying at night and armed heavily enough to shred enemy bombers in seconds. No. 157 Squadron began operational patrols in December 1941, intercepting German raiders over Britain. The Mosquito night fighters were devastating, fast enough to overtake Ju-88s and E-111s, agile enough to follow evasive maneuvers, and lethal enough to down their targets with single boast. By late 1942, Bomber Command's Pathfinder Force had adopted the Mosquito for target marking, dropping incendiaries and flares over objectives to guide the heavy bomber streams. The job demanded aircraft that were fast, precise, and survivable, and none fit that description better than the Wooden Wonder. That could reach the target first, survive the heaviest offenses, and mark with pinpoint accuracy. Mosquitoes fitted with oboe radar navigation systems could drop markers within 100 yards of the aiming point from 28,000 feet. On the 5th of March, 1943, during the raid on Essen, Mosquito Pathfinders illuminated the Krupp armament works so precisely that following bombers achieved unprecedented concentration, inflicting catastrophic damage on German industry. Photo reconnaissance variants stripped out all armament, replacing guns with cameras and extra fuel tanks. The PRMKI could climb to 42,000 feet, altitude where most German fighters struggled to operate, and surveyed targets across occupied Europe. These unarmed Mosquitoes depended entirely on speed and altitude for survival. Between 1942 and 1945, they flew thousands of sorties with loss rates below 1%. They photographed V-weapon sites, assessed bombing results, tracked naval movements, and provided critical intelligence conventional reconnaissance aircraft couldn't gather without unacceptable casualties. The anti-shipping and tank-busting variants pushed adaptation even further. Engineers mounted a 57mm Moulins gun, essentially a 6-pounder anti-tank cannon, in the nose of the FBMK-18. This Tetsi model could punch holes through U-boat hulls or destroy locomotives with a single round. Coastal Command Mosquitoes patrolling the Bay of Biscay sank 52 German submarines between 1943 and 1945. The FBMK-6 carried 8 rocket projectiles under its wings, each capable of piercing tank armor. These aircraft provided devastating close air support during the Normandy invasion, smashing German armor that threatened to halt the Allied advance. The Amiens prison raid on the 18th of February, 1944, Operation Jericho, showcased a precision and control only Mosquitoes could deliver. 19 aircraft from numbers 464, 487, and 21 squadrons flew 300 miles at treetop height, arriving exactly on schedule and dropping 500-pound bombs with delayed fuses directly into the prison walls. The first wave blew breaches through the perimeter, the second destroyed the guard quarters, and the third struck the main buildings. Of 832 prisoners, 258 escaped, among them 12 French resistance members scheduled for execution that very afternoon. 2 Mosquitoes were lost, one to flak and one that struck the wall during the attack. When German intelligence examined the wreckage of crashed Mosquitoes in 1942, disbelief was their first reaction. Investigators found no aluminum frames, only layers of wood bonded with glue. Luftwaffe engineers assumed these must be training aircraft or experimental gliders, not frontline bombers crossing Germany with impunity. But reconnaissance photos soon confirmed squadrons of Mosquitoes operating from IAF bases across Britain. The Raiheer Ministry had to ask an uncomfortable question. Had Germany's obsession with metal construction blinded it to a better material? Kurt Tank, chief designer at Focke-Wulf, was ordered in late 1942 to develop Germany's own Wooden Wonder. The Ta-154 project began with high hopes, a night fighter that could match the Mosquito's performance using timber instead of scarce aluminum. Tank's team studied captured Mosquito fragments, photographed the structure, and tried to replicate its mold-ply techniques. The first prototype flew on the 7th of July, 1943, reaching 404 miles per hour at 18,000 feet, slightly faster than the Mosquito. Tank was confident he had succeeded. But scaling the design revealed a vast difference between imitation and understanding. De Havilland had spent years perfecting adhesives, testing bonds, and enforcing strict quality control. Britain's furniture industry had generations of experience with laminated wood. Germany's war factories did not. Their expertise lay in machining, welding, and heat-treating metal. Craftsmen skilled in wood joinery had been drafted or reassigned to build pontoons and boat parts. The adhesive problem proved fatal. German chemists created Tego film, a phenolic resin they claimed matched British casein glues. Early tests looked encouraging, and production Ta-154s began rolling out in June 1944. Then the failure started. The Tego film reacted unpredictably with the beechwood Germany use in place of birch. Heat and moisture caused lamination, plywood layers peeling apart in flight. On the 28th of June, 1944, a Ta-154 broke up mid-air, killing the pilot. Investigation revealed the wing had separated when the adhesive bond failed catastrophically. Production was halted immediately. Worse, Allied bombing had destroyed the only Tego film plant, leaving no tested alternative. Substitutes existed but required months of evaluation, time Germany no longer had. With Allied forces advancing and resources vanishing, the program was cancelled in November 1944. Total Ta-154 production, about 50 aircraft. Operational impact, negligible. Other German wooden aircraft projects fared no better. The Heinkulhe 162 Volksjäger, Germany's desperate attempt to produce jet fighters from wood, suffered the same fatal adhesive failures. The Blom and Vos BV-40, a wooden glider designed to ram Allied bombers, never progressed beyond testing. Every German wooden aircraft venture collapsed under identical problems. Poor adhesives, too few skilled craftsmen familiar with laminated construction, and a lack of industrial infrastructure to support large-scale wooden manufacturing. These failures underscored what made the Mosquito truly revolutionary. The choice of wood was only the beginning. De Havilland's achievement rested on decades of manufacturing knowledge, chemical engineering that perfected adhesives through relentless testing, and a network of quality control ensuring every bond met precise standards. Germany could imitate the idea but not the ecosystem that made it viable. The Mosquito wasn't fast merely because it was wooden. It was fast because British engineers understood wood so thoroughly they could make it outperform metal. Production of the Mosquito continued until November 1950, 5 years after the war's end. The numbers spoke for themselves. 7,781 aircraft built across dozens of variants in Britain, Canada, and Australia. Among British combat aircraft, only the Spitfire, Hurricane, and Lancaster surpassed that total. For a design the Air Ministry had once dismissed as a furniture maker's fantasy, its success was an extraordinary vindication. Even more telling were the survival statistics. Loss rates for Mosquito operations averaged just 1.8 to 2%, compared with 3.5% for Lancasters and 4.1% for B-17 Flying Fortresses. Between 1942 and 1945, Mosquito squadrons flew over 28,000 sorties, dropped nearly 27,000 tons of bombs, and destroyed or damaged thousands of locomotives, vehicles, ships, and installations, all with minimal armament, proving that speed and altitude offered better protection than any gun turret. The aircraft Geoffrey de Havilland had designed to save aluminum ended up saving lives. Mosquito crews enjoyed survival odds far superior to those flying heavier, more protected bombers. Post-war analysis confronted the Air Ministry with uncomfortable truths. The Mosquito's triumph came precisely because it defied orthodoxy. Officials had rejected wooden construction because everyone knew metal was better. They had scoffed at the idea of an unarmed bomber because everyone knew defensive guns were essential. They doubted claims of fighter-like speed because everyone knew bombers had to be slow. De Havilland succeeded by ignoring what everyone knew and trusting physics instead. Though post-war aviation never returned to wooden A-frames, jet propulsion and supersonic flight demanded metals and new alloys, the Mosquito's philosophy endured. Its emphasis on speed over armament influenced Cold War bombers like the English Electric Canberra and the B-58 Hustler, both designed on the principle that velocity was the best defense. Its multi-role adaptability, one A-frame serving as bomber, fighter, reconnaissance, and strike aircraft, became standard practice for later generations. The F-4 Phantom, F-111, and Tornado all followed intellectually from the Mosquito's lesson that versatility could rival specialization. Its manufacturing legacy was equally profound. The Mosquito proved that wartime production didn't have to rely solely on heavy industry. Furniture factories, piano makers, and cabinet workshops built Mosquito components while metal plants focused on fighters and heavy bombers. Modern composite engineering, carbon fiber, Kevlar, fiberglass, still follows principles de Havilland's team pioneered with birch and balsa, laminated structures, geodetic molds, adhesive bonds stronger than the base material. Those 1940s innovations evolved into 21st century composites, but the science remains the same. Perhaps the Mosquito's greatest legacy lies in what it taught about innovation under pressure. In 1940, Britain faced extinction and material shortage. Conventional thinking demanded more of the same: more metal bombers, more guns, more armor. De Havilland proposed the opposite: less metal, fewer guns, no armor, just speed through ingenuity. His willingness to question accepted truths turned desperation into dominance. The wooden wonder became proof that the most dangerous phrase in engineering isn't "we tried that and it failed," but "everyone knows that won't work." Sometimes, everyone is wrong, and a furniture maker from Hertfordshire ends up understanding aerodynamics better than the experts who rejected him 3 times before letting him prove them spectacularly mistaken.